part D, we're going to start off with a different situation than the last couple times. We'll have a closed system with a number of moles in the vapor phase and the Gibbs energy of the vapor phase, as well as a number of moles in the liquid phase and the Gibbs energy of the liquid phase. It's important to know for this system that it's at a constant temperature and pressure, and that will be important for part 2 of this. But the first thing we should notice is that the overall change, so D and G, is going to be equal to 0. And because it's constant, a closed system, and the temperature and pressure are not changing. So another thing that's important is the number of moles is going to be constant. So the differential of that would also be 0, meaning that the change of the moles from the liquid to the vapor phase can be represented as dNV would be equal to the negative of D and L. And that's where we start. So if we were to add these together, that would make up Ng. So we can start there. Ng is equal to Nv times Gv plus Nl times Gl. And if we were to take the differential of this, we get dNg is equal to dNv times Gv plus dGv times Nv plus dNL plus dNL GL plus dGL times NL. Now that we have this, we know that dNv and dNL are just equal but the opposite sign. So we find our dNL and our dNv, meaning in this situation, this would become a negative dNv. So that could be simplified to dNv times Gv minus GL, and then plus dGv Nv plus dGL NL, which would be equal to 0 because, as we know, D and G is equal to 0. And that's where this equation we found earlier is going to become important, because we know there's a constant temperature and pressure, meaning that these will all be equal to 0 as this changes. 0, 0, these become 0, meaning that this is eliminated, and it shows that our D and V times Gv minus GL is equal to 0. And because this is a constant, it means that our Gv minus GL have to be 0, or that Gv of the vapor phase is equal to the Gibbs energy of the liquid phase for a closed system with constant temperature and pressure. And now we'll move on to part 2. Okay, before we move on to part 2, I noticed something, and is that I miscopied our equation for Gibbs energy, and this should have been VDP instead of PDV, which I mistakenly had it originally. It still leads us to the same conclusion of the Gibbs energy of the vapor phase is equal to the Gibbs energy of the liquid phase. However, it would just be switched here, meaning that when pressure is constant, this actually is a 0, and that's right up for that. So we're led to the same conclusion. Now we can move on to part 2, in which we can start off with our Gibbs of the vapor is equal to the Gibbs of the liquid. And we'll take the differential amount of this. And now we can plug in our equation, which we have. So minus S V dt plus V dP, hopefully it's correct this time, is equal, or SV and then VV dP, then minus SL dt plus VL dP. So what we can do now is we can transfer them on the opposite sides to get a more simplified version. So we have our VV minus VL times dP is equal to SV minus SL times dt. Now if we throw these onto the other sides of the equations, we get our dP over dt is equal to SV minus SL over VV minus VL. And now that we know we have this, we can use this equation to substitute for our dS's, which we have. So because we know our pressure is constant, that would also make this constant, and that means the differential would be 0, meaning that can be eliminated. And if we throw our t on the other side here, we have our ds is equal to dH over t. So we can substitute that in for what we have done here. So that will end us up with dP over dt is equal to HV minus HL over T times VV minus VL And what we know about this difference is that can just be represented by the total change, so delta H vat. And it's important to note that these are both volumes, and because the volume of the vapor phase would be so much larger in comparison to the volume of the liquid phase, in this situation, we can consider this to be a negligible amount and just call this V. And as we know, V is equal to RT over P. So that will get us dP over dt is equal to P times delta heat of vaporization over RT squared. And if we were to multiply by dt and divide by P, we would get dP over P is equal to, and then we'll pull out the delta H vaporization and our R, because those will both be constants in this situation. Delta H vat over R times dt over T squared. And if we were to integrate this from P1 to P2, and this from T1 to T2, we would end up with our Clapeyron equation, which would be, using some simple calculus, we get the ln of P2 over P1 is equal to delta HVAP over R times 1 over T2 minus 1 over T1. And that's how proving the Gibbs energy of the vapor and liquid phase are equal in a constant temperature and pressure system that's closed can lead us to our equation for the Clapeyron.